Morning. Here to present our research paper entitled An Ensemble Machine Learning Approach for Time Series Forecasting of COVID-19 Cases. I'm Renato R. Maaliw III, presenting this research paper in behalf of my co-authors as seen on. For the introduction, COVID-19 or the 2019 novel coronavirus has spread swiftly. It infects a million and it halts the global economic activity. As of the paper's writing, the overall infection is over 180 million, 3.9 million deaths, maybe more at present time. And the virus are seen resurging on different parts of the world and in different countries. So financial analysts conclude that the outbreak has had a detrimental effect on the international economy, has seen a 4% decline in GDP. 4% in GDP is a lot. Governments and policymakers face an uphill battle, devising steps to combat the outbreak while tolerating the extreme economic and health implications. Authorities in epidemiology they recommend undertaking advanced statistical data analysis to make informed decisions. So they stress the importance of investing more on accurate forecasting model than on investing on contact tracing. It's essential to determine specific steps that safely suppresses the virus while having the fewest possible adverse effect on people's health and economic well-being. Forecasting immediately enables decision makers and planners to make more informed decisions during current and future pandemics. So there have been numerous forecasting strategies have been proposed as a result of data science advancement. The most popular one is the SRI model. It takes infection and recovery rate into account, but in reality, it oversimplifies a complex pathological process. So its model hyperparameters involve many assumptions that are not true in actual cases. Why? Because individual behavior is impossible to quantify dynamically during a real world outbreak. So there's also judgment forecasting, but this forecasting methodology is heavily influenced by human prejudices. These are well thought out of by expert but are less reliable than quantitative models based on the literature. And only it is only prescribed as a last resort when data is incomplete or not available at all. While time series models so attempt to determine epidemiological behavior using actual historical data, forecast epidemiological activities using concrete data with fewer assumptions. So they are reasonably straightforward to explain to the general public due to their simplicity, but they mainly rely on the concept of non-linearity. Examples are exponential smoothing, moving averages, and ARIMA. Recent research has showed that machine learning can be adopted for disease growth foresight. So we address the limitation of epidemiological models, which rely heavily on assumption to its hyperparameters and the linearity of statistical methods by building a model centered on ensemble learning. Advanced prediction models that can handle non-linearity are crucial in assisting public healthcare providers and policymakers in determining effective plans to cope with the influx of infection. For the main contribution of our research, so we develop an accurate ensemble forecasting framework by combining the distinctive strengths of mathematical and deep learning models to handle complex patterns for time series predictions using normalized exponential weighted algorithm. For the methodology, our data sets are stable versions of time series data for four countries: Philippines, United States, India, and Brazil from March 8, 2020, June 18, 2021, acquired from the CSSE of Johns Hopkins University for infected and death cases. So this is the time series plots for the four countries. So first plot for infected cases and death cases. For the transformation and train test split and models, So for deep learning models, we scaled the data as a pre-processing technique. So for our train test split, so 80% training, 20% testing, over a year of data for 467 days. We use models of mathematical models of ARIMA and stack long short-term memory networks and ensemble model, which is the combination of ARIMA and stack LSTM for benchmark purposes. We forecast a 15-day horizon for infected and death cases. So we will forecast that. First method, we use stationarity test. So we perform a AD Fuller test to check the nature of the time series. This is important because this test reveals the stationarity of the time series, if it's a non-stationary or stationary, if it will exhibit a trend and seasonality. So also, we have the trend and seasonality decomposition as a methodology. So we decompose the time series as a structured approach. So this is also very important to know what are the hyperparameters that will be set for the given models. We use a trend decomposition and seasonality decomposition. As you can see, for the seasonality decomposition, there's a trend that every weekends, Saturday or Sunday, COVID-19 cases and death cases a decline. This is understandable as most workforce stay during weekdays at home. We also use the ARIMA for benchmarking purposes. So this is the most popular model for time series prediction. It has an AR, an I component, and a moving average component. So because of the complexity of setting the hyperparameters by reading autocorrelation function and partial autocorrelation function graphs. So we use grid search in order to calculate the lowest archaic information criterion. You can see at the table to the configuration. So we also use long short-term memory because LSTMs can overcome the limitation of conventional time series approaches by adapting to the nonlinear nature of data. It improves accuracy. It's a deep learning model. We also utilize the bidirectional LSTM. So it is an extended version of a regular LSTM or the unidirectional. So it is known to improve model performance. So it reads input sequences in both forward and backward directions. And we also utilize the long short-term memory by stacking. Stacking can model complex nonlinear sequences. So by stacking, so input observations are highly abstracted, recombining learned representation from previous layers. Bidirectional LSTM is a ideal candidate for the primary layers of the deep learning model. And we intentionally use the unidirectional LSTM for the last stack because for the final prediction, the model uses the forward directions only. So for the hyperparameter tuning of the stack LSTMs, so tuning is one of the most neglected part, but this is a very important part in training deep learning models. So we utilize auto tuning via scikit optimize for the sequential model-based optimization. You can see in table 3 are parameters that we have used for a stack LSTM. So we also plotted convergent loss plots for stacking and unstacking layers. So we would like to know the effects of stacking and unstacking layers. And also the number of epochs or the training runs that we will be used. So you can see the convergence loss plots. So in combining the ARIMA and stack LSTM, we use the normalized combinational algorithm, which is the weighted algorithm. So in which the best predictors of individual models will be weighted. So in simple terms, we gave different weights to standalone models before we combine because the different models is giving different prediction. So we prioritize giving more weight to the more accurate models. For the model evaluation metrics, we selected three in order to extensively evaluate the accuracy of the model: root mean square error, so mean absolute percentage error, and for the mean bias error on the equations. So for the results, so what are the effects of stacking and unstacking layers? We observed that the stack LSTM network, it takes time to reach equilibrium because we added additional layers compared to simple LSTM. So we also discovered that based on our data set, maximum of 3 layers or beyond 3 layers is not a guarantee to improve the performance. Also, we observed that decreasing amount of neurons for each layer are observed as the optimized settings. For the ensemble model, so these are the result of our optimal weights based on the weighted algorithm when combining the models. So except for the Philippines dataset, stack LSTM mostly dominated the optimal weights, as you can see on the table. Deep learning are robust in learning the underlying structure of a time series data. For the model fitness, these are the graph. Fit the model. Here are the result of comparative fitness. As you can see, stack LSTM is a good fit, but we cannot discount also the ARIMA because ARIMA is good in seasonality modeling. For the confirmed cases, it shows that the ensemble model achieves higher forecast accuracy for 4.13%, 10.51%, 4.39%, and 6.63%. For death cases, so again, the ensemble model achieve higher forecasting accuracy versus the standalone version models of 11.9, 17.22, 7.57, and 11.41%. For the bias estimation results, so different models generally over forecast the prediction except for the USA dataset. It under forecast. So it's still, although it over forecast, so the prediction is relatively closer to the actual values in terms of confirmed cases and death cases. So the study demonstrated the ensemble machine learning approach robustness in improving forecast accuracy beyond the capabilities of standalone models through extensive training procedures. Empirical results show that the ensemble models outperforms both ARIMA and SLSTM with the collective mean prediction accuracy for unseen data of 93.53% and 87.97% accuracy. So moreover, the ensemble model, it reduces the forecast error rates for confirmed mortality incidence by a combined 10.91% and 11.76% respectively. Time series is a very complex problem to tackle because of the different fluctuating trend, seasonality, and random noise factors. So our ensemble model's ability through integration of the unique strengths of various models coupled with comprehensive optimization strategies and a normalized weighted algorithm for model combination provides significant boost in forecast accuracy. So our results are comparable to the works of Sayed, Adhikari, Lamiri, Alaskar, and it provides a viable alternative to statistical methods as proven by the forecast accuracy. Again, for the limitation, as with any forecasting model, a sudden surge or immediate decline in the number of cases will force our model to over forecast or under forecast due to the related mitigating actions taken, such as lockdown and vaccination. Here are our graphical representation of prediction. So as you can see, the ensemble models outperforms the standalone models of ARIMA and deep learning model of stack long short-term memory for a 15-day forecasting horizon. For the conclusions and recommendation, so humanity is really confronting an unprecedented emergency health crisis in modern history. Up to now, we're still battling the COVID-19. So it requires extraordinary response from multidisciplinary collaboration. Therefore, accurate forecasting of confirmed and death cases gives vital information to governments and decision makers. So this inferential knowledge is helpful as it gives a broader and clearer perspective on the needed measures to slow down or eradicate the virus. Saves millions of precious lives if we know advanced inferential knowledge. So this research discovered the promising potential of ensemble machine learning approach in predicting modeling through combination of well-established mathematical and sophisticated deep learning. So we examined 467 days of data. It's March 8, 2020 for 4 countries. So it results show that our ensemble model combination of ARIMA and LSTEM outperforms the single models of ARIMA and LSTEM for unseen data with an average accuracy of 90.73% if you combine the death case prediction and the confirmed case prediction. So for the future work, we are planning to improve more the model's forecasting accuracy by exploring deep learning algorithms. We will consider recovery and vaccination rates, which is our also our essential data. Thank you very much for listening.